In the span of just 5 months, from October 2018 to March 2019, two brand new Boeing 737 MAX aircraft, Lion Air Flight 610 and Ethiopian Airlines Flight 302, plunged from the sky. A total of 346 lives were tragically lost. These weren't isolated incidents of mechanical failure, nor were they the result of typical human error. Instead, investigations uncovered a far more complex and disturbing narrative: a catastrophic interaction of a seemingly minor software feature, an incomplete safety system, and an aviation giant under immense pressure. We'll explore the real reasons, peeling back the layers of design, development, and regulatory oversight that led to this unprecedented disaster. To understand the MAX's fatal flaws, we must first appreciate its genesis. Boeing was facing an existential threat from its European rival, Airbus, and their highly successful A320neo, which promised greater fuel efficiency. Boeing needed a rapid response to maintain market share. The 737 MAX, an updated version of their most popular jet, was designed to compete directly, promising operators lower fuel consumption without requiring extensive pilot retraining. This drive for speed and commonality became a central, unseen architect of its eventual downfall, dictating design choices and compromises that would later prove catastrophic. The heart of the issue lay in a system known as MCAS, the Maneuvering Characteristics Augmentation System. Because the MAX featured larger, more forward-mounted engines compared to its predecessor, it had a tendency for the nose to pitch up in certain flight conditions. MCAS was designed to subtly correct this, pushing the nose down to give the aircraft the same handling characteristics as the older 737 models. Crucially, Boeing engineers developed MCAS to operate in the background, without pilots necessarily knowing about its existence or how to disable it. This hidden functionality became a ticking time bomb. The most egregious design flaw in the original MCAS implementation was its reliance on input from a single angle of attack, or AOA, sensor. This sensor measures the angle between the wing and the oncoming air. If this single sensor malfunctioned and sent erroneous data, indicating a false high angle of attack, MCAS would activate automatically, repeatedly pushing the plane's nose down, even when it wasn't necessary. There was no redundancy, no cross-check with a second sensor. This single point of failure transformed what was intended as a safety feature into a deadly vulnerability, a glaring oversight that defied fundamental aerospace safety principles. The consequences of these design flaws were devastating and far-reaching. The two crashes killed 346 people, 189 aboard Lion Air Flight 610 and 157 on Ethiopian Airlines Flight 302. Beyond the tragic human cost, the global grounding of the entire 737 MAX fleet lasted for an unprecedented 20 months, from March 2019 to November 2020. This resulted in billions of dollars in losses for Boeing, estimated at over $20 billion, including compensation to airlines, fines, and production stoppages. The grounding also led to the deferral or cancellation of hundreds of orders, forever altering Boeing's reputation and its standing in the commercial aviation market. On October 29, 2018, Lion Air Flight 610 departed Jakarta. Just minutes after takeoff, the aircraft began to experience erratic pitch movements, with the nose repeatedly forcing itself down. The pilots, unaware of MCAS or its activation, fought desperately to keep the plane airborne, following standard procedures to counteract a runaway stabilizer. However, the MCAS system, triggered by a faulty AOA sensor, continued to command nose-down inputs. The crew struggled for 11 minutes before ultimately losing control. The aircraft plunged into the Java Sea, killing all 189 people on board. It was a terrifying preview of a systemic flaw. A critical factor exacerbating the MCAS problem was the lack of pilot awareness and training. Boeing, driven by the desire for commonality with older 737 models, decided not to disclose the existence of MCAS in pilot flight manuals or require specific simulator training. The assumption was that MCAS operated subtly and autonomously. This meant that when MCAS malfunctioned, pilots had no prior knowledge of the system, nor specific procedures to counteract its aggressive inputs. They were essentially battling an unknown adversary within their own aircraft, relying on general emergency protocols that proved insufficient for this novel and persistent failure mode. Following the Lion Air crash, Boeing's initial response was to issue an operations manual bulletin, advising pilots on how to handle runaway stabilizer trim, a general procedure not specific to MCOS. They did not explicitly name MCOS or fully disclose its behavior. While investigations were underway, the company maintained confidence in the MAX safety. This cautious, some would say defensive, posture reflected a reluctance to admit to a fundamental design flaw, potentially underestimating the severity of the issue or prioritizing its reputation and existing order book. This delayed and incomplete response would later be heavily scrutinized, particularly after the second crash. Tragically, just 5 months after Lion Air, history repeated itself. On March 10, 2019, Ethiopian Airlines Flight 302 took off from Addis Ababa. Like Lion Air 610, it also experienced a faulty AOA sensor input, triggering MCOS. Despite the crew's heroic efforts to counter the system, including following the bulletin issued after the Lion Air crash, the continuous nose-down commands proved insurmountable. The aircraft crashed 6 minutes after takeoff, killing all 157 people on board. This second, eerily similar accident removed all doubt. This was a systemic problem, not an isolated incident. The world watched in horror as the global grounding began. The differences in pilot training philosophies between the legacy 737 Next Generation (NG) and the MAX played a crucial role. For the NG, pilots were extensively trained on all major systems and potential failures. With the MAX, Boeing insisted that the aircraft handle identically to the NG, therefore requiring only minimal, computer-based training updates. This approach, championed for its cost-saving benefits to airlines, meant critical new systems like MCOS were not adequately explained. The tragic outcome underscores a fundamental truth: complex new technology, even if designed to enhance safety, demands comprehensive training, not just a promise of commonality. After the second crash and the subsequent global grounding, Boeing was forced to address the MCOS issue comprehensively. The mandated software update for the 737 MAX significantly revised MCOS. Now, the system takes input from both angle of attack sensors, rather than just one. If the two sensors disagree by more than a certain threshold, MCOS is disabled. Furthermore, MCOS will only activate once per AOA event and with limited authority, allowing pilots to easily override it using the control column. This fundamental redesign acknowledges the original system's catastrophic flaws, but came at an immense cost. A critical layer of failure involved the regulatory process itself, specifically the FAA's System of Organization Designation Authorization, ODA. This program allowed Boeing to perform much of its own safety certification, with FAA oversight. While ODA is intended to streamline certification for trusted manufacturers, in the case of the MAX, it led to the FAA having an incomplete understanding of MCOS and its potential dangers. Pressures to accelerate the MAX approval, driven by the Airbus competition, further compromised the integrity of the review process. This reliance on the manufacturer to self-police created a dangerous gap in independent scrutiny. The speed at which the 737 MAX was developed highlights the commercial pressures at play. Boeing aimed for a short development cycle, largely due to intense competition from Airbus's A320neo, which entered service in 2014. The MAX was launched in 2011 and certified in 2017, a mere 6-year turnaround. This rapid pace, coupled with the imperative to ensure commonality with the 737 NG, allowed for the minimal disclosure of MCOS and insufficient pilot training. The drive to quickly bring a competitive product to market and maintain profit margins demonstrably overshadowed robust safety considerations in key areas of the aircraft's design and certification. At the core of many decisions was the imperative to minimize costs for airlines. By maintaining a high degree of commonality between the 737 NG and the MAX, Boeing promised airlines that their existing 737 pilots would require only short, computer-based training, avoiding expensive simulator sessions. This common type rating was a massive selling point. However, this commitment to commonality ironically led to the integration of MCOS without adequate disclosure or training. The decision to save airlines money on training ultimately cost lives, illustrating a dangerous trade-off between economic incentives and the highest standards of safety. The tragedies of the 737 MAX cannot be attributed to a single fault or individual. They represent a systemic breakdown across multiple levels. As industry experts have noted, the failures were a convergence of design errors, regulatory lapses, and corporate culture. Here's what one prominent aviation safety analyst had to say about the implications for the wider industry, emphasizing the long-term impact on trust and accountability. It's a sobering reflection on the complex ecosystem of modern aviation, where every choice, from the drawing board to the flight deck, carries immense responsibility and potential consequences. Adding another layer to this complex saga were the numerous whistleblower accounts and internal documents that surfaced during the investigations. These revealed a culture within Boeing that prioritized production speed over safety. Engineers and employees had raised concerns about the development process, the pressure to meet deadlines, and even specific issues with the MAX systems, including MCOS, long before the crashes. These warnings were, tragically, either ignored or inadequately addressed. This internal dissent underscores a pervasive issue where vital safety concerns were stifled or sidelined in the pursuit of commercial goals, leading to devastating outcomes. The decision to ground an entire fleet of commercial aircraft, especially a flagship model from an industry giant like Boeing, was unprecedented in modern aviation history. Initially, the FAA was hesitant, but after several other aviation authorities worldwide, including China and Europe, grounded their MAX fleets, the pressure became immense. The FAA ultimately followed suit, marking a moment of global consensus on the severity of the crisis. This collective action underscored the loss of trust not only in Boeing but also in the FAA's initial assessment, forcing a complete re-evaluation of the aircraft's safety and certification process. The two Boeing 737 MAX crashes were not due to a single, isolated factor but a confluence of interconnected failures. The investigation revealed a disturbing chain of events and decisions that cumulatively led to the catastrophe. It's critical to understand these layers to prevent such a tragedy from recurring. The lessons learned here are not just for Boeing, but for the entire aerospace industry, emphasizing the need for robust design, comprehensive training, stringent oversight, and an unwavering commitment to safety as the paramount priority. Here are the key layers of failure identified by investigators. Today, the Boeing 737 MAX has returned to service, but it's a different aircraft. The software has been fundamentally redesigned, and pilots receive comprehensive training on MCOS. Boeing itself has undergone significant changes in leadership and internal safety protocols, albeit under intense scrutiny. Yet, the road to fully rebuilding public trust and the trust of airlines remains long. The crashes serve as a stark reminder that even in the most advanced industries, human systems, corporate pressures, and regulatory mechanisms are just as critical as the engineering itself. Aviation safety is a continuous, collective endeavor, not a fixed state. In summary, the real reason Boeing's 737 MAX crashed twice was not a single mechanical failure or pilot error, but a tragic cascade of systemic issues. It began with the hurried development of a critical flight control system, MCOS, designed to hide the aircraft's new aerodynamic characteristics. This system relied on a single, vulnerable sensor, and its existence was deliberately concealed from pilots, exacerbated by regulatory oversight that allowed Boeing to self-certify key aspects. These crashes are a profound lesson in the perils of prioritizing commercial expediency over transparent safety, and the vital role of independent, rigorous oversight in safeguarding lives in the skies. The story of the Boeing 737 MAX is a powerful cautionary tale for the entire aerospace industry. It has prompted significant reforms, pushing for greater transparency, stronger regulatory scrutiny, and a renewed focus on safety culture above all else. As we move forward, the hope is that these tragedies, though devastating, will serve as a permanent catalyst for change, ensuring that the skies remain the safest place to travel. What are your thoughts on this complex issue? Share your perspectives in the comments below. If you found this deep dive insightful, please like this video and subscribe for more in-depth analyses of critical global topics.